Hello, good people. Welcome to my talk. Welcome to DevCom 2021. Today I'll talk to you a little bit about game AI, and I hope this will be of interest to you. First, I'll introduce myself. My name is Rafal. I work at QED Software as a game AI programmer. I'm experienced in traffic simulation for mobile simulator games. And then I switched to tactical and strategic games, but there's also more. And in my years in QED Software, I've worked on Grail AI framework, which I'll briefly introduce today, but mostly this talk will be focused on other topics. So first, I'll discuss popular game AI algorithms that you may already know, or maybe some of them will be new to you. And then after summarizing them, I'll stress the importance of a multi-algorithm approach to game AI. And then I propose a whole AI system architecture that we use in our company and that we use in our Grail framework. Then I'll quickly summarize two major problems that are still unsolved by us and that we're actively working on. So first, what do we mean by game AI? Game AI is a blanket term that encapsulates many different classes of algorithms: navigation, movement, perception, steering, all this kind of stuff. But today I'll mostly focus on decision making because I think that is the most interesting part of game AI, of course. So what challenges do we face when implementing game AI? First, our agents have to work in environments that are very diverse, and additionally they are subject to frequent change because, as you all probably know, the game production process is very iterative. So the game changes all the time, the requirements change all the time, and your agents have to be maybe don't have to readily adapt to those changes, but they should be easy to modify to accommodate to these changes. So another important challenge is automatic testing, because most of you and most of software companies, most of game companies focus on manual testing by human testers, and it's very expensive, cumbersome. There are multiple different diverse kinds of agents in more complex games, and we want to reuse as much code as possible while still providing the diversity of behaviors. And of course, a point that's related to the testing problem. We deal with a very wide range of situations, so our agents have to behave properly, even if in situations that the AI designers couldn't have expected. So out of those challenges, these concrete requirements emerge. First, we need our systems to be modular. We don't want any hard coupling between external systems and our game AI, between different AI algorithms. We want everything to be modular so that it could be tested properly. The point that's related to that is that we want to easily mock different parts of our agents. For example, if we want to test movement, we don't want any high-level AI decision-making processes to interfere with our testing of movement, because it can lead to many unforeseen problems. And as soon as we have some behaviors implemented or our decision-making techniques, we want to reuse them as frequently as possible, and it would be the best if we could reuse them between different agents. Okay. So first, I'll start with a brief overview of currently used game AI techniques. So don't expect anything very in depth. I just want to paint a broad picture of techniques that are used by game AI developers. So first, I'll start with the technique that's very old, and probably all of you know this technique. It's used in game AI, but also in animation systems. So probably I would bet that like 100% of you have already seen this technique, namely finite state machines. So we model our agents' behaviors as so-called states, and our agents, of course, can perform only a single behavior at a time. And then those states are connected with transitions that are associated with handcrafted conditions, like if my health is smaller than 50, then I pass from this state to another state, and if I see an enemy, that I start fighting, etc. And it's a cool technique. It works for simple agents, but for more complex behaviors, it gets very cumbersome due to the necessity of management of all this transition between various states. Adding new behaviors is very problematic. So this technique works well only for very simple behaviors. And over the years, people tried to various techniques to improve the inner workings of finite state machines by introducing hierarchization. And in Halo, I don't remember the year of the release of this game, but it's been for a while. This technique has been present for a while. The developers proposed a technique called behavior trees, which you also might know. I would bet that most of you at least have heard about this technique. So the basic building blocks of behavior trees are tasks. Those leaf nodes that you can see on this diagram are individual tasks. You can think of them as atomic actions, and each of those actions can return a status. And those status can be ongoing, failed, or successful. Basically 3. We have also a special kind of task node, which is a condition node, that just checks a single condition and returns success or failure. Then we have higher level composite tasks like sequences and selectors. So sequences just iterate over the atomic tasks that are in its child nodes, and just proceed till the end unless there is a failure somewhere on the way. Whenever there is a failure, the whole sequence returns a failure. And there's a selector node which performs its child behavior also from left to right, but as soon as it stumbles upon a successful behavior, it terminates. So this is the most basic implementation of behavior trees. There are, of course, this technique is some maybe 15 years old. I don't remember exactly, but it's pretty old. So it's been improved upon by adding various node decorators and some improvements like this. But this is the basic outline of the algorithm. The behavior trees have some problems because when you introduce a complex situation with many decision parameters, it leads to a lot of boilerplate. Like you have to add a lot of condition nodes, then jumping between different sub-branches of the behavior tree becomes very cumbersome. For example, whenever a new opportunity arises and we would like to change to a wholly different behavior, but we're stuck somewhere down in the behavior tree, we have to define so-called interrupts, decorator nodes on this behavior, and it's just very cumbersome. It's very difficult to design and to reason about. So to respond to those problems, another reactive AI technique emerged. It's called utility AI, and the whole model of this reasoning technique is much simpler, because on the highest level we just think about our agent as a container for behaviors, and each of these behaviors is coupled with a scorer, I should say, or evaluator that ranks this behavior or evaluates the utility of the single behavior, and then we select the best of all those. So because we don't have any formal hierarchical structures and any binding between those different behaviors, we can easily terminate one of them and then switch to another one and then switch to another one. It makes it all very easy. So there are three basic blocks of there are three basic building blocks of utility AI, namely considerations. Those are components that evaluate single world state parameters, like for example agent health or distance from a medkit. There are curves which transform outputs from our considerations into another floating number, which we call a score. And then because there can be many curves associated with a single behavior, we have to somehow aggregate them into a single utility score. So we aggregate those scores by minimum, by maximum, and other possible methods. Right. So here's a diagram that summarizes this technique. First, at the top of the picture, there are two considerations. Namely distance, a distance, for example, from an enemy or from some kind of pickable booth like medkit or something. And here, because this concrete evaluator is taken from our game, which is named Tactical Troops, and which is a tactical games when you have action points. So those action points also are a consideration in this game. Then the consideration values are passed through curves, evaluated, and then aggregated in this example by minimum. So you have a system where there are many such evaluators. Each of those are coupled with behaviors, and the one that scores the highest is chosen as the current behavior of our agent. And this approach has many advantages. It may produce unexpectedly complex behavior, even with very simple configurations. For example, you can have 4 behaviors with 2 curves each, something simple like this. And even in unexpected situations, the agent may behave really intelligently, because when you design AI, you may have some concrete situations in mind, and you form those utility curves to fit those situations. But whenever something unexpected happens, because the curves are mostly continuous, the agent will interpolate between those situations that you predicted when designing. Debugging of these systems is very easy, because you just can list all those scores, all those consideration evaluators, and just see for yourself what happened inside the brain of the agent. So it's very easy to debug. You can much more easily than in behavior trees, you can combine many decision parameters without introducing unnecessary boilerplate, like those condition nodes and interrupts and all kinds of stuff. And it's very easy to remove or add new behaviors, because you don't have any explicit coupling between different behaviors. So you just add a behavior, stitch an evaluator to it, and you're done. And finally, I think that the most important advantage of this technique is that you can model agent's personality by moving those curves around. For example, if you want an aggressive agent, you just take an attack evaluator curve and move it upwards. If you want the agent to be peaceful, you move it downwards. So you can reuse pretty much the same configuration topology, but tweak some parameters, some curve parameters, and get a wholly different behavior. But sometimes we want our behaviors to be not only purely reactive, based on the current world state. Sometimes we want our agents to think also about the future. And for this purpose, we use various planning techniques. You might have heard about goal-oriented action planning, for example, used in Fear and other games. So basically, planning problems amount to constructing an initial world state, and then applying various actions to this world state and imagining different possible states. And of course, to talk about planning, we have to provide the planner with a goal state that we want to achieve. So the thing that AI designers should do is just define actions with so-called preconditions and effects. Preconditions are the conditions that allow for the action to be executed. For example, you can make a bow if you have a stick and a string. So this will be an example of preconditions. And effects are just modifications of the game state in response to this action. And each action additionally can be, but doesn't have to be, associated with a cost. For example, you can model behaviors that are time consuming by assigning a higher cost to them. So let's see an example of constructing a plan space. We start with an initial state marked in purple here, and then based on this world state we can construct a set of legal actions, meaning those actions whose preconditions are met in this concrete state. And then we can simulate applying those actions to the state, creating another state, then we can repeat those operations on those children states and produce deeper states. So for now this structure is very tree-like because there are no cycles, but as you can see those rightmost states are identical, so we can merge them and produce a general graph. And of course, various graph problems are well known in computer science. So for example, if you want to find a goal state starting from an initial state, it's basically a pathfinding problem, but on a very specific space. So you can reuse all your pathfinding algorithms to deal with planning, just with some slight modifications. There are four basic advantages of planning. First, it is goal-driven, so it for your users, for the players, and those agents that can plan really seem very intelligent because they can see that they have purpose, that they don't simply react to external stimuli, but they just they have some sense of the future. It's very easy to design because you define those actions, you define goal states, and you're done. And the whole behavior is emergent. And it's very easy to expand. Similarly, it's a difficult word, to utility AI. You just add a new action with its preconditions, effects, and costs, and basically you're done, and the system goes from there. All right. So there are situations when you have agents that have to play well, not only behave realistically or believably, but have to play really well. For example, in tactical games or strategic games, RTS games, and you to do so in such adversarial environments, you have to somehow simulate the possible actions of your opponents, and for this. In the board game world or combinatorial game world, and there's in 2007, so quite recently, a new algorithm has been proposed called MCTS, meaning Monte Carlo Tree Search. And it's basically a game tree search technique similar to techniques like minimax or maximin, whichever you may like. But its special feature is that it's not deterministic. It searches the tree stochastically. And it's very famous from a project called AlphaGo by DeepMind, I believe, which was able to win with professional Go players. Using this technique, augmented with machine learning techniques, of course. And here's the basic outline of Monte Carlo Tree Search. We start with selection, where we start with a current state. Then we have some legal actions, very similar to that we have in planners. We can apply those actions, thereby adding new nodes to the game tree. And we do so until we fall out of the tree, till we reach the leaf node. And if there are actions still possible in the leaf node, we select a single one by a special algorithm called UCT, meaning upper confidence bound applied to trees. I won't go into details of this concrete technique because you can. I don't want to lose too much time on such details. You can Google it basically, and then after we add such new state. Instead of digging down until we reach the end of the game in a controlled fashion, we just perform a simulation, a random walk. A random walk down the tree, just selecting those actions at random and checking what will happen. And then after we reach the end of the game or some other predetermined termination condition, we evaluate the leaf state and propagate the score of this state upwards. So and we build statistics, like basically there are two main statistics in this technique. One is the number of visits in those nodes, which tells you that, oh, this sub-branch of this tree is very, very promising because it's been visited very frequently during the simulation. And then we also have mean scores. I mean that there are basically quality evaluations of each of those nodes, and by correspondence of each of those actions. It's a really cool technique because you can iterate, go over this cycle as much as you want. It can be, of course, limited by your computational budget, so you can adjust the amount of iterations to your specific requirements. As I mentioned before, the main advantage is that you can easily simulate behaviors of your opponents, even multiple opponents. If you give the technique enough iterations, it converges to optimal solutions. But if you want to terminate early, maybe you won't stumble upon an optimal solution, but it will be good enough. And in combinatorial games like chess, checkers, or all sorts of stuff, even Go, as I mentioned, you cannot really get any better. Unless you use general machine learning techniques like deep neural networks, which of course you don't have time to do. All right, so I've outlined many different decision-making algorithms for you. So now I'll try to say a little bit about about connecting them in some way. First, I start about quick discussion of tools that are available on the market. We have a lot of tools for low-level stuff like navigation, movement, steering, obstacle avoidance, all this kind of stuff that you typically use when steering your agents. There are some tools for behavior trees and FSMs. Even in Unreal, there's a built-in tool for designing behavior trees. There are many other tools for finite state machines. For other techniques that I mentioned, there are some cryptic, even open source tools for planning, for utility AI. For MCTS, I was not able to find anything that could be of use in games, but those tools are typically very focused on single techniques, and still doesn't solve our problem that we have many different techniques that we want to use for different subsets of our game. And there is our own AI framework that we developed in QED software, and this talk is based on the architecture that we used in the framework. It's called Grail. You can see the logo somewhere above my head, I believe that it solves some of the problems that we have, but not all, which I also discuss at the end of the presentation. Okay, so how can we merge those various algorithms? First, we'll start with some requirements. First, we want to share results between them. For example, we have a high-level AI using MCTS in a strategic game. For example, you can have a simplified representation of your level as a graph, and you want to simulate grouping of your troops, moving them from node to node, and then simulate what your enemy can do, and make very high-level decisions like take this, overtake this node, or take over, I should say. Take over this node or attack this base. Those kind of very, very high-level decisions, you can make them with, for example, MCTS. And then you want some lower-level AIs that would really execute those orders. They have to have easy access to the results of the high-level reasoning process. We want to reuse behaviors as much as possible. For example, imagine a typical behavior tree tool. You have a behavior defined, and it's merged with the decision-making process. So you cannot easily take this behavior tree and use it as a planner action or something like this. Typically, in most of game tools, of game AI tools. And there's an emerging need for a unified architecture that would let you do those things, communicate between different algorithms, and to reuse behaviors. here's a real-world example to envision why such thing is even needed. For example, it's a tactical game. The individual playouts are very short because it's like one single game lasts for 10 minutes, but it's very action dense in our game. And unfortunately, I don't have any slides to show you the game by itself, but you can Google it and check for yourself. But what's most important in the game is that we have 3 basic AI layers. First one is dealing only with goal selection. For example, attack this unit, or take over this control point, or destroy this object, this kind of things. So the top level AI doesn't perform any real world action. It just decides upon different goals. Then there's a layer that performs detailed action planning and simulates opponent actions with MCTS, and then the results from this middle layer are interpreted by low-level unit AI that and individual units don't have many degrees of freedom, but as soon as the unit receives its order, it can perform so low-level actions like a position adjustment, this kind of stuff. There are many challenges when trying to design such a system. First, we have to deal with inter-algorithm communication, and we don't want to introduce like hard-coded coupling. We don't want our behavior trees to depend on utility AI, and we don't want our utility AI to depend on behavior trees. Like, we want to use those techniques for various domains, for various decision-making layers. Don't want any hard couplings between them. We want to easily switch algorithms during runtime or configurations even. For example, imagine a boss fight. When you have a boss that completely changes their behavior during the fight. So you can, of course, design a huge behavior tree that and deactivate and activate the various sub-branches, but you can also design wholly different decision-making algorithms for this purpose. And you want just to switch the boss's brain. We want to often coordinate different parts of the decision-making process. As I mentioned in tactical troops example, we have 3 AI layers, and each subsequent layer has to wait for the high layer to finish its computation. And there's another challenge. Namely communication with various external systems. Of course, you know that you have to, when you make a decision to perform a behavior, you have to somehow tell the lower level systems like navigation to move the agent. You can need some environment queries. For example, you can look for good obstacles or cover points, and those systems have to communicate well without explicit reliance on a concrete system, so that it can be changed later easily without impacting the AI. So now I'll propose the architecture that we use in our products that I think solves most of those challenges, of those problems. There are 4 basic blocks. I'm talking weirdly again. There are 4 basic building blocks of our architecture, namely behaviors. And behaviors, you all know how to interpret this word. It's a single action performed by an agent. It can be very simple, like atomic single action, like walk from this point to this point, or maybe very complex. Those may be behavior sequences or even whole behavior trees. There are AI entities, and these entities are responsible only for executing behavior. They don't deal with any decision-making process. They just receive the behavior and perform it, and tick this behavior, simulate this behavior. Then there are reasoners, and these are high-level representations of decision-making algorithms. For example, you can have a utility AI reasoner and a planner reasoner, a behavior tree reasoner, these kinds of things, and they are dealing only with selecting best behaviors given a situation. And then we have AI managers. There can be many AI managers, and their responsibility is to trigger decision-making processes and tick AI entities behaviors. And you have to, and it's important to stress that AI entity is not the same thing as a game character, because you can have a single character that's driven by multiple entities, like you can have a movement behavior that's wholly independent from shooting behaviors or target selection, for example, in a twin stick shooter. Or you can have a single entity that governs behaviors of many characters, like think of a simple tactical combat, like in Heroes of Might and Magic. You have some units that are fairly simple, so they don't need their own decision processes, and you have a single like godlike entity on the top that manages behaviors of individual characters. And the interface of AI entity class is fairly simple. You can set a reasoner, you can set a behavior, get this behavior, and execute it. So, as you can see, the entity is dealing only with behavior execution. Behaviors, in turn, can be started, updated, finished, and there are some helper functions for this. They can here in this function you can check whether the behavior is finished. Here it can be delegalized, because you often want to differentiate between behaviors that are finished successfully and unsuccessfully. Similarly to what you've seen in behavior trees. Some behaviors can be marked as interruptible or not interruptible, meaning that if you're in the middle of a long animation, you don't want those behaviors to be interrupted. And we can get a status of behavior. So it can be ongoing, it can be failed, it can be successfully completed, all these sorts of stuff. Then there are reasoners, which are very on the interface part. They are very simple. They accept an AI entity and then select the best behavior for this concrete entity. AI managers, as I said before, there are just ticking mechanisms for our AI, so you can register various entities in those managers, remove them, update reasoners, and update entities. And those two functions at the bottom, they are purposefully separated, because sometimes you want your decision-making processes to be triggered very rarely, but still want to tick individual behaviors more frequently. So here's a basic game character construction in our architecture. Imagine a character that has some behaviors or decision making problems related to movement, to target selection and interaction with the environment, and also you can have some kind of top level AI that coordinates actions of those lower level ones. So for such an agent, we'd create 3 different AI entities, each with its own reasoner and with its own behavior sets. So when we have such an agent, sometimes we just want those AI entities to run in parallel without even communicating with each other. But most of the time, we want some kind of coordination, and we have to exchange information between those different entities. And to do this, we use so-called blackboard structures. Some of you may know them from behavior trees in Unreal, because they are used there to communicate between behavior tree tasks, individual tasks, to transfer data from a single behavior, atomic behavior, to another ones. And so we just generalized this approach to enable not only communication between different behaviors, but also different entities and such. Each of our AI entities has an associated private blackboard where you can store their private information, private beliefs about the world state, and you can store other kinds of common data, like some global dependencies on shared blackboards. and blackboards can be shared between definite groups of entities, or they can be assigned to AI managers when any entity can access them. For example, if you want some game data, like lists of units that are on the map, you don't want each entity to have it on their private blackboards. You'd rather want to place this kind of data on a globally accessible blackboard in a game manager, in an AI manager. So as soon as we introduce the blackboard concept, we have to extend our AI entities interface by methods related to getting, adding, and accessing blackboards, shared and private. So here's an extension on the tactical troops example. Here's our basic architecture outline for the bot in this game. First, we have a strategic layer that selects high-level goals, and its only responsibility is to write some data on a blackboard that's later used by lower layers. So this AI layer doesn't perform any specific actions in the game world. It just selects the best goal for a specific unit and writes this goal to a blackboard. Then a lower level of AI takes those orders and interprets them and computes specific actions for each unit. And then each unit is assigned an action via a private blackboard. And then unit AIs can perform execute those orders as best as they can. Another example of the usefulness of blackboard data structures is interaction with external systems. For example, environment query systems. You can have a behavior sequence that starts with some initial actions, simple actions. Then you can have a more complex behavior that relies on, for example, an environment query like cover point, like seeking of cover points. So we introduce a special behavior that writes this query data on the entity's blackboard and then just waits. And our environment query system can iterate over each entity, gather query data, perform all those queries in a batch, which is much more performant, and then just return the results back to those blackboards. So there are a few very important benefits of this architecture. First, which was stated as a goal explicitly, there is no hard coupling between different entities and decision-making algorithms. You can reuse whole AI entities between different characters. For example, if you designed a general movement decision-making entity, you can reuse this concrete entity between different characters that have different behaviors on higher levels or parallel levels, but you can reuse whole AI configurations. Reasoning algorithms depend only on data stored on blackboards, so it's very easy to test them, modify them in any way. For example, if you have a global dependency, like for example this mentioned environment query system, you can just throw out this whole environment query system and replace it with a simple script, so that you can easily test the agent's behavior without reliance on various global dependency chains. Another important feature is that action selection and action execution are separated, so you can even test single behaviors by assigning them directly to an entity without relying on a decision-making algorithm. So again, testing is very important. So this allows for more granular testing of our AI systems. Level of detail. This is something that I've only mentioned in passing, or maybe even I forgot to mention. There's an important problem in game AI when you have a lot of agents, and some of them are remote. They are very far away from the player, and you want them to be ticked less frequently than those who are closer. So you can do this, or even you may want them to exhibit simpler behaviors when they are far away. So you can do this by changing whole reasoners. because you can do this very easily, just call in one function. You can switch the whole reasoner to a simpler one, or you can use a different AI manager that ticks those behaviors, those entities less frequently. And of course, in these systems, integration of other AI techniques, not only implemented by us, but also by third parties, it is very trivial, because you just wrap the decision-making technique with a reasoner, and basically you are done. And because there is no explicit reliance on our classes. Okay, so what's next? I'll talk about for a little bit about problems that are still unsolved that we are working on now. First one is dealing with imperfect information, because many of those techniques rely on some informational structure, some data structure that is assumed to be known. But in games we frequently have limited access to information, like lines of sight, limited senses. And the data that our agents can register is very heterogeneous. For example, they can be position sets or symbolic representation of the game world. It's very diverse, and typically it's done in a very game-specific fashion. Developers just implement tailor-made solutions for their specific game, and we think that it can be generalized. So we are now working on a unified belief formation framework that's completely separate from the decision-making part of the system. And we include many different techniques, like rule-based reasoning, Bayesian reasoning about the game world. You can plug your own prediction heuristics into the system, and we want it to be fully interoperable. And then I think that's a song of the future that will work in the future, is merging those individual agent beliefs into collective beliefs, so that we can dynamically form groups of agents that behave intelligently. All right. And there's another, this will be the last two slides. We will talk about some problems related to game testing. As I have said many times before, our AI has to function in very diverse environments, and it's very hard to assess AI quality because of this. Because your testers can detect some weird behaviors in concrete situations, or maybe even they are content with the behavior of your AI in concrete situations, but there are some that go undetected until your release. So we want to automate the quality assurance process for AI. So now in QED software we're working on machine learning models that are trained on logs from games, like for example a position log, where you have positions of the agent over time that can be later analyzed by our models. And we can use those models to, for example, assess quality of game bots by, for example, comparing it to human gameplay. We may want to train our models to extrapolate user feedback. For example, you can watch a short clip of AI behavior, then rate it, for example, on a scale from 0 to 1, and then learn our models which kinds of behaviors are basically good, let's say good, and which kinds of behavior are sorry, I forgot the right word for this, so I'll say bad. And an additional use case, maybe it will become one of main use cases for these models, is cheater detection. Because if we manage to train models that can detect suspicious or anomalous behavior in games, we can use them to detect cheaters or bots in multiplayer games. So it can be of value also in these applications. Okay, if you want to learn more about our system, you can check the web for Grail AI framework. I encourage you to participate in the Q&A session after this talk, but if you have some proposals or larger questions or about specifics, technical specifics, you can also write me an email, and please do visit our websites listed here. Okay, so that will be all for today. Thank you for your attention and patience, and have a nice day.